your screen?
Yes, so, I'm using a tablet, so I'm going to share my tablet.
Yes,
It's
perfect.
going to work.
Yes, that works perfectly fine. So yeah, it's my great pleasure to introduce Dan Crisan of Imperial College, London, who's going to speak about the well-posedness properties for a stochastic rotating shallow water model. So Dan, the floor is yours.
Thank you very much. And can I thank the organizers for the invite to talk at this meeting. I've never realized that SPDs have so many friends. Yeah, it's great to talk to an audience that is not just purely SPDs, but also to talk to the friends of SPDs. My talk, you know, I'm trying to make some connections with the previous talks, and there will be a bit of connections. I'll try to mention that. But you know, it's really about an SPD that is a stochastic version of the rotating shallow water equation. And so what I plan to do is, first of all, I'll explain what the shallow water model is in a rotating frame, so that you can see where the SPD is coming from. And then I'll spend some time explaining the choice of the noise, which is going to be quite unusual and quite different from the type of noises that we in the SPD community are used to have. You know, it's not an additive noise, it's not a multiplicative noise. You know, you'll see what it is. And I will also explain why this particular choice. And this is really grounded in physical principles, and that's sort of kind of the guiding principle of this work that I'm doing to try to model sort of oceans using SPDs. And so I will then sort of give the formal definition of local, maximal, and global solution of the SPD. I'll give the main results. There's just going to be two main results, and then depending on how much time do I have, I will talk about proofs. This is joint work with my former students, Juana Lang from Imperial, who's now PDRA at Imperial, and it's part of his thesis, and it's part of a paper that is now in preparation. We are in the final stages of the writing the paper. Hopefully we'll get it out by the end of the month. And also I should mention that this research is partially supported by an ERC synergy grant, and I will hope to have some time towards the end of my talk to say a little bit about that and offer an open invite for people from this audience to join us and talk to our group. Just to double check, I came late, and in the program it said that I would start at 11 o'clock CET, but you know, possibly I will. The program has been delayed. Am I right?
Yes, we are a bit late, but you have 35 minutes in total.
You mean 45 minutes in total? But I mean, I thought my slot is for about an hour. Am I right?
So Oleg of the organizers told me that you would have 35 minutes and then the discussant 15 minutes. So perhaps the organizers can comment here. But that's the information I have.
I can comment. I don't mind if you take 5 minutes.
No, but you guys, anyway, there is a big break. So if you have a little bit more material, you can talk for 40 minutes maybe. So,
okay.
So there is like a big break. So 40 minutes is okay.
Good.
All right, thank you. Right, okay, let me get on with it. So let me try to introduce the shallow water model, and I think that the first thing that it will impress anybody who's coming from the theoretical side of the SPD. SPD is sort of, in some sense, the messiness of the model, and you know, you have to live with that. That you know, models get in real life, models can get very complicated and very quickly, and so but because I'm coming from the theoretical side of the area, you will see that it's going to be I will do my best to try to simplify the model as much as possible, so that you know we get back to the things that we can understand and work with. So let me just explain what the model is. So imagine you have an ocean, and you know you slice the ocean at some level. Let's call this level z equal to 0. So z is sort of the vertical axis, so that you are still underwater. So the idea is that at all points in the slice, there's water above you, and you're going to look at two things. So the variables here will be the horizontal velocity. So you, instead of looking at a 3D model, you look at sort of a 2D model. You just look at the horizontal velocity of the fluid on this horizontal slide. And then you look at the thickness of the fluid column. So the thickness of the fluid column is this thing from here, from the bottom of the ocean to the top of the fluid, and you assume that there is the bottom of the ocean is not flat, but there is a topography. That's what is called the bottom of the ocean. There is a topography. And the thing which is going to be quite important is there's another constant here, which is b, right? And so obviously this b is always going to be positive. And what's going to be important will be the difference, this difference between h and b, and this difference between h and b will influence the velocity. It will appear in equation satisfied by the velocity as a pressure term. So it appears in here as a pressure term, as a forcing term in some sense. So u and h are the variables. So let me explain the equation satisfied by u. This is the equation satisfied by u. So we have a differential term, and this differential term has two parts. One is the derivative with respect to time, and another one is a nonlinear term, is u dot grad. In fact, this differential term in there is the derivative of u with respect to time plus u dot grad u plus and so on. And it's written like this because in fluid dynamics, this has a name. This is called the material derivative. It's not going to bear any importance in the analysis of this for a physical perspective is put together, because the way you think of this is that is the derivative along the trajectory of a particle of fluid. So we have this material derivative of u, to which you add a term which models the rotation. So this is a sort of, from a PDE perspective, this is just a zero order term. You take the cross product between the vertical direction and u, and you multiply it by a constant f, which is the Coriolis parameter. And we're going to assume that f is constant. It doesn't make any difference if you take a different f in there. And then you have this additional kind of forcing term, which is coming as an effect of the amount of fluid that is on top of the slice. and the sum of all of this is equal to 0. So that's the equation satisfied by U. And then you have the equation satisfied by H, which is just the mass continuity equation, which is written like this. So this is the usual d by dt of H plus, so this is the divergence of ht times ut. This is equal to 0. So these are the two equations that describe the shallow water model. Now there's some parameters in here. Excuse me. So the first parameter is this epsilon, which measures the intensity of the rotation, the effect of the rotation. And there's another parameter f, which appears in here, which is the flow number, which measures the effect of the pressure. So this is the evolution equation for the rotating shallow water model. So now let me go on and tell you a little bit about the properties of this model. And it's really a very nice model. It's easier to analyze than the 3D primitive equations. For, in case you don't know, the primitive equations are sort of the equation of choice for modeling the atmospheres and oceans. And you know, there's lots of simplifications here, but some of the key aspects of these models of atmospheric and ocean models are still preserved. So one thing which is preserved is that allows for gravity waves. So these are some low frequency waves that are really quite important in modeling the weather and climate, because they allow for the transition of energy from one part of the planet to another part. And there are some theoretical properties that are also quite important, and in the sense that it's a variational model, in the sense that you can construct an action function, and this if you take the variational derivative of this action function, the solution, the critical point of this action function is characterized by the solution of this equation. And also, quite important, it preserves the circulation around the closed curve. And this is something which is really very important. You kind of expect these things for fluids. Before I say anything about this, there's some alternative versions of the model that I just shown you. You can do a transformation where you define a new velocity as being this epsilon, this velocity number times u plus another constant r, which comes from the rotation, and then you can rewrite the equation either in this form, and this is the form that you'll see in a minute. This is the first step in trying to simplify the model, or in this form. This form is really important because it is this form that helps us characterize, it helps us justify that the variational derivative of this action function is characterized by this equation. So when I go to the circulation in here, this says that if you take this velocity v, and then you integrate this velocity around a contour, and then you look and see what happens at the subsequent time t. So you wait for a time, you look at where the contour arrives as a result of the motion of the fluid, and then you integrate the same velocity around this new contour. This is constant. So this is really something which is quite important, and there's a lot of in fluid dynamics. This is a very important property. Okay, so what we want to do is to say, okay, now we have the deterministic model, so we want to add some stochasticity to this deterministic model, not just have an ad hoc way to add stochasticity, but to try to have a meaningful a physically meaningful stochastic perturbation of the rotating shallow model. And the idea here is that instead of adding stochasticity at the level of the SPD, you add stochasticity at the level of the path. So imagine that you have a path of fluid, you have a particular fluid that evolves according to this compound velocity. So what you do, you say, okay, we're going to perturb this path with some stochastic term here, and I'm going to go and sort of explain what the stochastic term is on the next page. So you see, I'm perturbing these particles, the path of the particles of fluid like this, and then I'm asking the question, okay, what is the actual equation that will have this property if you look at the particles of fluid, and they satisfy this particular SD. So the reason why do we want to do this? First of all, because it seems in some sense natural to perturb the particles of fluid, but also because the stochastic version of the rotating shallow model, this stochastic version will still satisfy some the critical path for a stochastically perturbed action function, and it will preserve the circulation around the cause curve, where the cause curve is now moving according to this new velocity. Okay, and from a sort of the reason for the perturbation is because we want to say, okay, we're going to work with this model on some certain core scale, and these perturbation models, what's left out, the smaller scale, the influence of the smaller scale. And this methodology is called the stochastic advection by leaf transport. Methodology is called SALT and was introduced by my colleague Dario Korn in a paper in 2015 called Variational Principle for Stochastic Fluid Dynamics. And we've written together with one of my students an extension of this paper where we replace these Brownian motions by arbitrary martingales, and in addition to that, and this is the connection that may make the friends of SPDs interesting. In this, we've written a paper that does this when these Brownian motions that appear in here are replaced by rough paths. And this is a paper that we finished not a long time ago, and it's available on the archive. And then we use the results in here. We use the methodology in here to deduce rough PDEs, and we deduce the rough Euler equation, and we analyze its properties in a paper that again we finished recently, and it's again available on archive. So for people that are interested in rough PDs, I recommend looking at these two papers. They are really very interesting papers, and we're really hoping that, in particular, this paper here will make up a bridge between the rough path community and the fluid dynamics community. It's really very important that these two communities begin to talk to each other. And if you read the paper, you will see why this is important. Okay, so as I said, because I'm coming from the theoretical side, when I saw how messy the model was, I said, okay, we need to clean this model. And so what I did is I'm rewriting this model that we saw on the first page in a much simplified way, like this. So I'm putting together the two variables v and h, right? And then I'm saying, okay, the deterministic rotating shallow equation can be written in this way. I put together all the messiness into this common function f, and the common function f applied to v and h has this expression. So all I did, I just say, well, we're looking at an equation that looks like this, dAt plus f of at dt. So, I'm writing the differential form because in a minute I'll add stochasticity to it. I didn't need to. And f has this form. And in here, there's a notation in here, which is this notation here, which is kind of a sort of lead derivative or is, if you want a sort of u dot grad b explicitly written in there. So what we do, we are taking this now very clean version of, we're taking this very clean version of the rotating initial order model and add stochasticity. So what we will analyze will be, this is a deterministic bit, and then we will analyze, we will add this stochasticity in here, and I'm going to have to tell you what these GIs are. So we sum up a countable set of stochastic integrals with a coefficient that I need to tell you what it is. And in the first instance, these stochastic integrals are a Stochanovich form. Now, in addition to that, we will add some viscosity term in here, mu times Laplacian AT, because this is going to make the analysis work. And obviously, this is something that we want to look in the future and try to see if we can eliminate the viscous stuff. Okay, so in order to explain precisely what the model is, I need to tell you what these GIs are. So what are the GIs? So this is the model in here. Okay, so the GIs are written in here. Okay, so the part that applies to V has two operators. One is this Li. So this is a first order differential term, right? So you can think of it as a sort of transport in the direction of some given vector fields psi I. And the second one is a zero order term. It's a zero order term where you multiply the components of the velocity by these gradients of these psi i's that are in here. Okay, and so then the next thing is to explain what is the what is the diffusion term for the H component. It looks like this. It looks like this. So if you want, it's in some sense just the adjoint of psi dot grad H. Okay, so I'm not going to. It's a first order. It's sort of a mixed term in there, and this is the simplest way to write this term. Okay, so I'm still assuming that the integrals in one are of Stochanovich type, and now you can really see how different this is, right? So rather than starting with a given additive noise, multiplicative noise, and so on, if you say, okay, how do we do this in a meaningful way, in the physical meaningful way, you end up with this noise, which you could perhaps never thought that this is the right noise that you need to use. Okay, so that's this is the SPD. So I'm going to tell you quickly what is the how do we define the solution. So the solution now, this system will not be globally well-posed. It's just going to be locally well-posed. And a local solution means that we will have a pair where this tau is a stopping time, a strictly positive bounded stopping time, and A is the solution. And the solution is only going to be defined up to the stopping time. And you will the first component of the solution, that means the velocity, will take value in the Sobolev space W12, and the second component will take value in the Sobolev space W22. So we have an extra degree of smoothness for the second component for H. And then what I've written in here, exactly the solution that is the equation that we saw on the previous page, except is written in integral form up to the stopping time tau. And the only thing that is changed is that we replace the Stochanovich integrals on the previous stage by ether integrals, and therefore we change the drift term so that we add the correction coming from we have the ether correction. Okay, so that's the equation. That's the local solution, and then basically If it happens that the local solution is up to infinity, in other words, the stopping time is infinite, then we say that the solution is global. Okay, now the maximum solution is basically what you get if you piece together local solution. So the maximum solution again is a pair between a stopping time and the solution, which is made out of limits of local solutions. You get local solutions A tau n. This stopping times tau n will have a limit. This capital tau is the limit, and you're gonna want to assume that this maximum stopping time is strictly positive with probability 1, and the part that really characterizes the fact that this is a maximum solution is that should this stopping time is be finite, then the W1 to norm of AT is infinite, and that's really quite an important thing, that you cannot go beyond it because you'll be exploded by the time you reach the stopping time. And there's a remark in here which says that yes, that's the case, that somehow this a stopping time that satisfies this definition is really a maximum time. In other words, you cannot extend it. Okay, so a few remarks in here. One remark is that we want to work with the Ito or not with Satonovich, and the reason for that is that if you are to work with the Satonovich version, then because of sort of technical properties that you want to have the integrand in the Satonovich integral being a same martingale, you need to assume additional smoothness on the initial condition. And because this is a stochastic analysis community, we understand that, and we are happy to put up with that. But if you go and work with talk to the pure PD fluid dynamics people, they say it means that your solution is suboptimal because you ask for more smoothness than it is required in the chemistry case to so that you have a local well-posedness. Okay, so the theorem. So this is the first theorem. The first theorem, it says that indeed there is a local solution. Okay, provided the initial condition is in this space. Okay, tau is a strictly positive stopping time, and by doing this piecing together, there is a unique strong maximum solution of the system. More than that, the solution depends continuously on the initial condition. So any small variation in the initial condition will result in small variation of the solution at any subsequent time t, as long as the solution exists at that time. Okay, so when you first start looking at these things, the first thing that you do is say, okay, we're gonna go ahead and apply standard techniques. You go and say, well, we have Dabdato-Jarczyk, we have Rockner, we have a lot of standard arguments which you can apply, and it turns out that you can't. And the reason for that is that these operator GIs that appear in the stochastic perturbations are actually not Lipschitz in any norm that you choose. And so because of that, it is quite hard to apply any standard results. So we had to come up with a new methodology. Now the new methodology, I'm not sure if it's been used before. I'm not sure if anybody else has tried that. It's an energy method which is based on a linearization of the SPDV, and the linear equation uses some classical results introduced by Rozowski. So we use as a fundamental methodology the work of Rozowski. So if you want, in something, this is an extension of Rozowski's work. Okay, and so the way in which this is done is sort of kind of standard, with relative compactness results based on a priori estimates, and so, as I said, we want to introduce some approximate sequence of solutions. Okay, So a few remarks in here. So this is a lot to take in. Let me just say that the reason why we introduced the viscosity term, why introduced the Laplacian, is because of this gradient of P that appears in there. So this gradient of P is the thing that kind of messes up things very quickly. And the Laplacian, essentially what it does, it sort of kind of handles this gradient of P. What you normally do, you try to look at controlling certain Sobolev norms, and then when you try to do control the Sobolev norms, because of this gradient of P, it looks like you always have to look for the next norm up and the next norm up and so on. But once you introduce the Laplacian, you can in some sense close the system. So that's the idea. The addition of the Laplacian makes the whole analysis work. Now, the one thing which is quite important for those of you that work with SPDs that are only locally well-posed, that only exist up to a certain local time, you can't take expectation of the solution at any time t, because if t is larger than the blow-up time, then you don't know what that is. So the only thing that we can do always, we have to work with localized version of the SPDs. You have to work with integrals up to some stopping time, which is less than the blow-up time. So this makes things very difficult from an analytical perspective, and I put here some of the things that you hit when you try to do the analysis. For example, the standard deterministic Grunwald approach doesn't work and cannot be used to control the Sobolev norms and so on and so forth.
Sorry, Dan, just to remind you, there's about 10 minutes left until you reach 40.
All right. Okay, then. Thank you. So, I told you about the properties of the local solution. Now, the only thing that I'd like to add here is that what can you say about this maximal stopping time? The first thing, which is really quite important, is that it's strictly positive, right? So at all time, the solution exists for at least a little bit of time. And we also show that if you choose the initial condition to be small enough, and we have clearly, we show how small it has to be, then the solution is actually global with positive probability. And in the deterministic case, basically, there is no randomness, there is no probability there. So, the corresponding result in the deterministic case is that for a small initial datum, the solution is global. Here, we have to handle these situations that because the randomness can make things quite difficult to handle. And even though no matter how small you choose your initial condition, the argument that you use can only show that you end up with a global solution with positive probability. And I have some explanation here that explains why in the deterministic case you are able to show the global existence for small initial data. Okay, now we are now working hard to try and find a way to find a different argument by which we can actually show that the solution for small initial datum, the solution is global with probability 1, and we don't have yet a complete argument, so that's what we're working to try and show now. Okay, so in the remaining minutes, I'm just gonna give you a little bit of what the argument entails. So the argument uses a truncation of the model. Okay, so what you do, you take the nonlinear parts and you truncate the nonlinear parts, right? So the SPD has a nonlinear part and each of the nonlinear parts gets truncated by this function of the sums of the W1 to norm above the velocity and the height. And this function basically is, the standard truncating function. It's equal to 1 on some interval 0 capital R, equal to 0 on R plus 1 to infinity, and sort of decays smoothly between 1 and 0 on the interval R plus 1. So the idea is in here is that because of this truncation, somehow the possible blow up of the nonlinear term is handled. So you make this nonlinear term, you can control this nonlinear term nicely in terms of the W2 to norm of the solution. So you can start beginning to use Reynolds inequality and so on. So the theorem in here is as follows: that once you truncate, so this is exactly the system that we saw before, but you truncate the nonlinear terms. Once you truncate, then you end up with a unique global solution. That's the idea. More than that, if you look up the stopping time where the truncation begins to take place, you look up to the stopping times when FR is no longer 1, then obviously this is going to be 1. So the solution of this truncated equation is the solution of the original equation. So the idea is what you do, you piece together the solutions of the original equation by using the solution of this truncated equation and using the fact that any two of these truncated equation could coincide up to the minimum of the truncations. Okay, so basically that's the theorem that justifies this. If you put together these truncations, you get the maximal solution of the original equation. Okay, so one thing, and then I'll stop. How do you show that the truncated equation has a solution? The way you do that is, as I said, by linearizing. So the way you linearize, I've written here separately. Here is where, so this is just still the original, the truncated equation, but I'm changing the drift. And in the drift, the thing that gets changed is again the nonlinear term. So what you do, you take a sequence, okay? You start with some trivial initial value for the sequence, some constant value, and then the sequence at time n uses the sequence at time, the value of the solution corresponding to the nth element of the sequence depends on the value of the solution corresponding to the nth minus 1 element of the solutions. By putting all of these things in here, you put n minus 1 instead of n. And that makes the whole thing linear, and then we can apply estimates of the Stochastic for the truncated sequence, show that it's relatively compact, and so on and so forth. Okay, I'm not going to go through this anymore. I'm just going to show you, advertise this network that I'm part of. Is based on a grant that myself and 3 other TIs have got, and we started last year. Can I encourage people to look at this website? And we've got lots of activities advertised, and we have some annual conferences which I invite people to come, people that are interested in doing SPDs and for fluid dynamics, people that may be interested in applying graph paths for fluid dynamics, come and talk to us. We are very keen to engage with the community at large. Thank you very much. I'll stop here.
Thank you very much, Dan, for this very nice talk and for the invitation. So I think we hand over to Michele, who is the discussant, and then we have some time for questions.
Okay, thank you, Tom. Let me share.
Yes, it's perfectly visible. So the stage is visible.
Okay, thank you. Okay, so in Dan's talk, we saw the rotating shallow water model, which is a fluid dynamic model where we have the assumptions on the velocity of the fluid, that the vertical component of the acceleration is negligible, so that vertically we have a constant velocity, and then and moreover the horizontal components of the velocity are independent of the z variable, so that we have this derivative is equal to 0. It means that, and this is due, these assumptions are done because we are because of the shallow property, so the velocity evolves only in an horizontal plane, so to say, because the vertical scales are smaller, so that now this is a function from R2 to R2. And then there is the vertical thickness of the water column that describes the third component in the equations. So Dan introduced, so the equation then is simplified to this one, where F is a deterministic nonlinear advective term, and it presents nonlinearities, which are given by these two terms. And moreover, the difficulty comes from the pressure terms, which because Dan studies a compressible fluid, so this guy enters in all the estimates, and which cannot be closed unless which can be closed by adding a viscosity to the equation. The noise that acts on this equation is of this Sol type, and which basically is required. The fundamental reason to use this type of noise is to preserve some physical properties of the system. So, okay, Dan described the noise term, which is linear, but it's not your standard transport noise. There are other terms coming in. And maybe you should note that here it's written in Stratonovich form, but the analysis is done in Ito form, plus the correction term that goes back here, because the Stratonovich requires this guy to be a local martingale, and you don't want, and this would impose additional regularity on the initial condition, which is undesirable. Okay, so the results obtained in the talk are about solutions. So first, the concept of local solution is introduced. So, which is a solution that is defined up to a bounded stopping time. The solutions that are investigated are in the Sobolev space 1, 2, 3. So the path of the solutions are in the Sobolev space. So the regularity of the initial condition is preserved. A solution is called global when the stopping time is infinity. And then a maximum solution is the limit of local solution, of increasing local solutions. And it is called maximal if after that the energy of the solution explodes. So the main result of Dan talk is a result about local well-posedness, and so there is a local existence for the solutions of this problem, but uniqueness, I put a star there because they are unique in the sense that if you have multiple local solutions, they coincide up to the common time of definition. And thanks to this, one can construct a unique maximal solution. Now, the one difficulty that comes in, and which is different from the corresponding deterministic model, is that the maximal, so that on some path there is a maximal solution, but for some other path there might be explosion. So thanks to the author is able to prove that the probability of non-explosion is bigger than 0, but it is still an open problem whether it is equal to 1 or not, and it is subject of future work. Now, the strategy to prove this we have seen is to add a truncation to the nonlinear term, and so such that when the energy reaches some threshold n, you simply truncate the nonlinear term out of the equation. So now for the equation where f is replaced by the truncated version, there is a result of global well-posedness, and to obtain this global well-posedness, one linearizes the nonlinear terms. And maybe a comment, so thanks to these truncations, there are global a priori estimates which depend on the truncation n. Okay, so, and once you have global well-posedness here, well, you just construct the solution up to when, so you define the solution of the original system equal to the truncated solution up to the time where the energy reaches the threshold n, and since since this solution coincide, so the solution an coincides with an minus 1 up to time tau n minus 1, you have a well-posedness also. So you have existence of local solutions and maximal solutions for the original system. Okay, I'm speeding up too much, maybe, I don't know, but we are late, so it's fine. So this stochastic advection by lead transport, which is called SALT. So this type of noise was introduced by Holmes, and the idea is that this noise is added to the system because it models small-scale processes which have a strong impact on the large-scale dynamics. But also this model preserves the physical properties of the underlying system. For instance, as you have seen in the talk, it preserves the circulation along closed curves. So as I was saying, it was formalized by Holmes in 2015, and maybe this kind of some transport noise. Maybe I want to point out that although in these talks is used to show well-posedness, it is also used to improve the regularity of the deterministic system. For instance, in these papers by Flandoli and Holm and co-authors. And the stochastic rotating shallow water model is used also in data simulations to work with real world problems in meteorology and oceanography. And maybe to conclude this very fast discussion, I want to point out these two previous results by the two authors, Dan Crisan and Oana Lang. So where they look at, so to say, simplified, more abstracted models before reaching this work in preparation that Dan discussed, which has much more properties of the real world applications. So in this previous work, they look at the 2D Euler vorticity equation for an uncompressible fluid in so an ideal uncompressible fluid. And so in particular, and they obtain for these global solutions whose paths have the same Sobolev regularity as the initial condition. And later they added to this model the modelization, so to say, of the bottom topology of the bottom topology of the fluid, and which you have seen also in the previous talk, in the present talk. So this bottom topology modifies the interaction between the vorticity and the velocity. And for this model, they obtain local solution in weighted Sobolev space, so with path in a weighted Sobolev space. But this equation still describes an incompressible fluid, so the pressure term doesn't play a role here and here. Whereas in today's talk, they are able to introduce a pressure term, which makes for a much difficult and more interesting from the application point of view analysis. Okay, with this, I will just stop the discussion here and thank you.
Yes, thank you, Michele, for the discussion. So before we continue with the question session, as before, I'd ask everybody to turn on their videos and give both Dan and Michele a round of applause for their talks. Well, thanks very much. Good, and now would be the time for questions. Okay, let me check chat.
Or maybe I can ask a question to Dan.
Yes.
So you need to add this viscosity term, but do you think you can let the viscosity go to 0 and obtain some results with the non-viscous equation?
Well, there's work which kind of explains. So we have this viscosity term because we are mathematicians and we like Laplacians.
Yes.
And because we like Laplacians, the first thing that we started to do is to say, okay, we just have this viscosity term. It may be possible to do that. Not with methodology that we have at the moment, because we use Rosowski's results, and Rosowski's results essentially do not work if you don't have this viscosity term. But we've been made aware of different viscosity terms where you avoid the viscosity in the second equation, in the equation for the height, but you use a different viscosity term in the equation for the velocity term, and it's not the usual Laplacian. It's something which is a bit more complicated and which makes sense from a physical perspective. So the first thing that we might want to do is to eliminate the viscosity in the height. The height is not really viscous, but keep a viscosity term in the equation for the velocity where you have some viscosity, but it's not the viscosity that we as mathematicians like what is a different type of viscosity. And then we might want to see if we can, in some sense, eliminate that viscosity, try to get something. But this is really farther down the field.
Okay, thank you.